What if light bends? Because it is smart. What if the ray of light knows its destination, and chooses the path that gets it there in the least time? Gottfried Wilhelm Leibniz lived in an age of reason, a cosmos of matter, motion, and mathematical law. But where Newton saw a mechanism, Leibniz saw a mirror. Reality, he claimed, was not made of atoms, but of monads, indivisible centers of perception. Each one a viewpoint, reflecting the entire universe from within. They never collide, never touch. They unfold their destinies in perfect, pre-established harmony, synchronized like instruments in a divine symphony. The universe was not a machine, it was a mind, a living computation, expressing itself through order. It was a radical idea, a glimmer of bit hidden within it, and it carried a startling conclusion: this must be, of all possible realities, the best possible world. Not morally best, but mathematically best, the most elegant, efficient, complete. Perfection itself could be written as an equation. If nature always acts by the simplest means, could that principle be made precise? Working in solitude, Leibniz forged a new language, a symbolic system for continuous change. He called it calculus differentialis. Tiny differences, flowing seamlessly into one another, could describe motion, growth, and transformation. It was as if he'd found the hidden grammar of becoming. Leibniz published first, but had someone discovered it earlier? Across the channel, Isaac Newton, reclusive, brilliant, and fiercely protective, had already devised his method of fluxions, a geometry of motion rooted in absolute space and force. His equations described quantities that flowed, driven by causes from the past, never by goals from the future. He saw no room for purpose, only for law. But the two men were bound by fate. Each glimpsed the same summit from a different mountain, and neither could bear to admit the other was right. Letters crossed oceans and decades, courtesies turned to accusations, accusations to silence. By the time the Royal Society convened an inquiry, mathematics itself had become a battlefield. And in a cruel twist, the very man accused, Newton, presided over the judgment. Leibniz was condemned, Newton was vindicated, Europe took sides. Pride became policy. But beneath the scandal, something far greater was at stake. To Newton, calculus was a tool of forces, a way to compute how matter obeys external pushes and pulls. To Leibniz, it was a logic of harmony, a language of relations unfolding by inner necessity. One saw nature moved by contact and cause. The other saw it guided by correspondence and reason. That fracture, between the mechanical and the harmonic, would echo through every science that followed. And a century later, a Frenchman would try to reconcile them. Pierre-Louis Moreau de Maupertuis took Leibniz's metaphysical dream and made it a physical law. He proposed that nature acts by a single rule of economy. Out of all imaginable trajectories between 2 points, a ray of light, a falling stone, a colliding planet, each takes the one that minimizes a quantity he called action. To Maupertuis, this was divine arithmetic. God's wisdom expressed as efficiency. The universe, he said, is not just lawful, it is optimal. But to others, it was heresy. How could blind matter choose a path? How could the future influence the present? Did Maupertuis dare to give nature a mind? In Paris, whispers spread. Was this science, or theology in disguise? The age of reason had little patience for divine whispers. Yet Maupertuis' idea refused to die. It suggested that every motion, every flicker of light or fall of stone, was part of a vast, unseen negotiation, the universe forever balancing cost against consequence. Nature, it seemed, had been given a goal. It wasn't merely pushed from the past, it was pulled toward perfection. Mechanism versus metaphysics. Order versus purpose. Two infinities colliding. Calculus was no longer just a tool. It was a bridge, between cause and consequence, between motion and meaning. The 17th century had given humanity mastery, but it had also planted a question. If the universe is a machine, then who winds the clock? Voltaire hated it. To him, Maupertuis' least action was nothing but mysticism disguised as science. The Enlightenment was at war with anything that smelled of purpose. When a rival claimed Leibniz had described it first, Voltaire saw his chance. The century's sharpest wit launched one of the most devastating satires in intellectual history. He mocked Maupertuis as a pompous mystic, sneering that, if light finds the shortest path, perhaps generals should consult it before marching to war. Was Julius Caesar minimizing action when he crossed the Rubicon? Did lovers optimize their trajectories when falling in love? The salons of Paris roared with laughter. Maupertuis fled into obscurity, his reputation destroyed. Mechanism had defeated purpose, or so it seemed. But ideas, unlike reputations, do not die so easily. While Maupertuis' name became a joke, his principle began a second life, not in philosophy, but in mathematics. Leonid Euler, the quiet titan of St. Petersburg, saw through the controversy to the clarity beneath. He realized that if nature truly seeks to minimize something, there must be a mathematical way to find what and how. In the 1740s, he forged the calculus of variations, a method for determining the exact path, curve, or surface that makes a quantity smallest or largest. It was Maupertuis' dream, stripped of divinity, reforged as pure analysis. To Euler, action was no longer divine purpose. It was geometry in motion, a universal bookkeeping of energy. Where Maupertuis had seen intention, Euler saw necessity. And then came Joseph Louis Lagrange. In 1788, he published Mécanique analytique, a work so sweeping that he opened it with the words, "No diagrams will be found in this book." He no longer needed Newton's forces or trajectories. Everything, planets, pendulums, particles, could be derived from a single line, L equals T, V. Kinetic energy minus potential energy. From that expression came the principle itself. The true motion of any system is the one that makes the total action stationary. No divine hand, no conscious choice, just mathematics, the language of efficiency. Where Maupertuis had sought proof of God, Lagrange found the foundation of physics. His equations described a universe that appeared to optimize itself, not through intention, but through inevitability. It was as if the cosmos had learned to think without thought. The laws of motion were no longer commands, they were solutions. Every orbit, every oscillation, every collision was now a silent calculation, the cosmos doing its own accounting, balancing energy like a ledger that never errs. Voltaire's laughter faded, Maupertuis' ghost remained, and his heresy became physics. In the end, both visions survived. The universe behaves as if it minimizes something, yet it does so through local, mindless rules. Each particle moves blindly, and together they compose a perfect symphony of efficiency. Leibniz had seen harmony, Newton, law. Neither was wrong, each was half the truth. Their quarrel over calculus wasn't a scandal of pride, but the opening act of a deeper question: how can a mechanical world give rise to purpose? How can the push of causes create the pull of elegance? How can a blind equation give birth to beauty? That question would haunt physics for 2 centuries, until a young patent clerk stepped onto the stage and asked if space and time themselves might bend to reason. Next time, the clockwork will break, the stage will tilt, and the universe will finally ask, not how it moves, but why it moves at all. Until then, keep questioning the fabric of reality.